know that brilliant, super durable color you see on a nice watch or maybe some kitchen faucets or even high-end tools? Well, guess what? It's not paint, it's not dye, it's something way, way cooler. Today, we're going to peel back the layers on the atomic art of physical vapor deposition, or PVD for short. We're going to see how science lets us literally paint with physics. So here's the big question, right? It's a problem that artists and engineers have obsessed over for, well, forever. How do you make something that's not only beautiful, but also lasts? What if the secret wasn't about finding a better pigment, but about bending the laws of physics to your will on a scale that's almost unimaginably small? And the answer to that question is this incredible technology called physical vapor deposition, PVD. Now, I know the name sounds super technical, but the core idea is actually elegant and simple. You take a solid material, say titanium, you zap it inside a vacuum chamber until it turns into a vapor, and then you let that vapor condense onto an object one single atom at a time. It's kind of like 3D printing a new surface, but on a scale so tiny it's just mind-boggling. All right, so let's dive right in. Section 1, the art of the atom. This is where we're going to see that PVD isn't just about slapping on a layer of color, it's about completely rebuilding a surface from the ground up. So to really get PVD, you have to completely forget everything you know about paint. See, paints and dyes work by absorbing some colors of light and reflecting others. PVD, it's a whole different ballgame. It's about creating a brand new surface structure that plays with light in a totally unique way. We're not just coloring an object, we're literally teaching its surface how to create its own color. So, if we're teaching a surface to make color, how on earth does that actually work? Well, that brings us to our second section, painting with pure light. This is where the real magic happens. And you'll see how PVD can create colors that are more vibrant and way more durable than any paint ever could be. You've definitely seen this in action before. Think about that shimmery rainbow effect on a soap bubble, or a little bit of oil on a puddle of water. That amazing visual is called thin film interference, and believe it or not, it's the exact same physics that PVD uses. Light waves hit this incredibly thin PVD layer and bounce off both the top and the bottom. When those reflected waves meet back up, they interfere with each other. Some color waves get canceled out and others get a massive boost. So by controlling the thickness of that layer with atomic precision, you can pick exactly which color you want to shine through. And this right here is the absolute key. Research from Watanabe really nails it. Because the color comes from the physical structure of the coating, not from a chemical dye, it just can't fade. The structure is the color. It's permanently built into the surface itself. Pretty cool, huh? But this atomic level control that PVD gives us goes way beyond just color. And that brings us to our third section, engineering surface and touch. The same exact principles that let us control light also let us design how a surface actually feels and behaves. The big idea here is something called surface morphology. It's just a fancy term for describing the shape of the surface at a microscopic level. Its landscape of tiny little peaks and valleys. By controlling exactly how those atoms land during the PVD process, we can build either a perfectly smooth, glassy plane or a really rugged, textured mountain range. And check this out. This shows you exactly why that matters. If you create a super smooth, flat morphology, what do you get? A high-gloss, mirror-like finish with pure, deep color, because the light just bounces right off cleanly. But if you engineer a textured morphology, you get this beautiful matte or satin finish. That texture scatters the light, which is perfect for creating anti-glare surfaces on your phone or your laptop. Plus, as a bonus, that microscopic roughness can actually help the coating grip onto the surface even tighter. Okay, this all leads us to our fourth section, and this is where things get really, really fascinating. Beauty with hidden benefits. It turns out that when you engineer the perfect look, you can also give a surface some pretty incredible superpowers. We all know this struggle. I mean, whether it's your smartphone screen, your glasses, or your kitchen sink, keeping things clean is just a constant battle against dirt and grime. But what if a surface could just clean itself? Well, there's a scientific term for this property, and it's super hydrophobic. It literally means extreme water-fearing. We actually see this kind of thing in nature all the time. Think about a lotus leaf. Water just beads up and rolls right off, and it takes every single speck of dirt with it. PVD lets us copy that effect and engineer it onto almost any material we want. So how does it work? It is just genius, really.
By using PVD to deposit these teeny tiny nanoparticles, you create a very specific kind of microscopic roughness. This texture is so fine that it traps a thin layer of air right against the surface. So when a water droplet lands, it's not even touching the surface itself. It's actually sitting on this tiny cushion of air. It can't spread out, it can't wet the material. Instead, it forms this perfect little sphere, and at the slightest tilt, it just zips right off, grabbing all the dust and dirt on its way out. So where is all of this technology heading? That brings us to our final section. The future is on the surface. Because this ability to design and build materials atom by atom is just blowing the doors wide open for a whole new world of material science.
And honestly, we're just scratching the surface here. Think about medical implants with PVD coatings that not only help the body accept them, but also look and feel better. Or what about eco-friendly self-cleaning coatings on buildings that get rid of the need for harsh cleaning chemicals? We're already seeing it in electronics with better anti-glare screens, and pretty soon we could have smart materials with sensors built right into their very surfaces. The possibilities are just absolutely extraordinary. So the big takeaway is this. The surfaces all around us are getting smarter, more beautiful, and way more functional. The next time you see a stunning metallic color or a surface that just magically stays clean, you'll know it's not magic. It's the art of applied physics. And it really makes you wonder, doesn't it? As we get better and better at this kind of atomic design, what will the world of tomorrow actually look, feel, and even act like?